So, hello everybody. This is Christophe and I'm Kevin. We both come from Criteo, which is a French company that does advertisement retargeting. And we are here to talk to you about debugging. So to give a bit of context, Criteo deals with 200 billion HTTP requests per day across more than 8,000 servers. And when you work at that scale, every tiny random bug, the kind that has less than 1% chance of happening, is absolutely guaranteed to occur on production server. So we are part of the Criteo Performance team. And as such, one of our jobs is to help developers diagnose and fix those issues when they happen on a production environment. And we thought that it would be nice to show you a few of our real-world investigations, because we noticed that no matter the type of issue that we investigate, the process to solve it is pretty much always the same. So the goal won't be to focus on the specific tools that we use to decide how they work, but rather to show you the methodology and also share the ideas and false leads that we had during the investigation and how everything led to the resolution. So I mentioned a process. It's very simple. Whenever you are facing an issue, the very first step is to gather as much information as possible. You can never have too much information, but it's really important to make sure that this is information that you trust. You have no idea how many hours we lost investigated issues, that was based on false data. When you have all your data, you still need to understand it. You need to put that into context. That's usually the step where you're going to use tools to get deeper data. And the goal of this step is to make a hypothesis about what is going on. And then there is the most important step, that is checking every single one of your assumptions, validate your hypothesis. And more often than not, you will find that they are wrong. And so you use your new insight to go back to step one and gather new data, and then try to understand it, make new hypotheses, and so on until you finally manage to solve the issue. So we're going to show you two cases that actually happened and that we had to investigate. And most of our investigations start from the monitoring dashboard.
Yeah, we are using this kind of dashboard that you can see here. It's mostly based on the performance counters that you can get on your Windows machine. And I won't spend some time describing each and every performance counters, but just to begin with the kind of investigation we are doing, we're usually starting from the end of something like you have a cause and you have a consequence, okay? And when you investigate something, it's at the end, okay? Something happens and you need to find the cause. So if we take a look at this one, for example, we have the CPU usage. And if we see a spike on CPU usage, what could be the reason? We could have a spike in exceptions. So if you have the exception thrown parameters there going wild, we know there is a correlation. So we'll try to find the correlation. We could also have a burst in allocation memory. And in that case, the garbage collector might kick in more often, take more CPU. So the one around garbage collection should move here. And you can have even weirder case where you are using like spin locks to guard your shared resources, and in that case, you will have some spinning in user mode before going into kernel mode, and the CPU will spike. So when I left university in 1989, after studying artificial intelligence and expert system, it was called abductive thinking. Okay, so we had the cat at the beginning, we have the buzzword, so now we can start something serious, okay? So this is the first investigation. We started with this curve. So again, you need to trust what you are seeing. And here, what we have, it's called the contention rate. So these performance counters count the number of time one thread tried to acquire a shared resources and another thread already got the resource. So it gets like contention. And what we can see here that starting the 15th of June, we have a change in the way we get contention. So before we get no contention, which is very good for scalability. And then starting there, we're saying in more and more contention. So what could be the cause of this contention?
So before jumping to your tool, just to try to understand as much as you can from your data. So for starters, we see that it started on June 15th. For this case, it was easy to understand what happened that day because we released a new version of one of the services. So obviously, we probably shipped a bug with it. Also, something very interesting about this curve is that it increased progressively across a few days. So it seems to indicate a leak of some kind. Also, it is not shown here, but the response time is stable, no impact at all. So that means that either the contention events are very short, or more likely they are occurring somewhere in the background. And last but not least, the memory consumption is stable. So it means that if we are leaking memory, we are leaking very small amounts of it. Okay. So that's about all we can deduce from it.
So at that stage, you have to stop a little bit and don't rush into your favorite debugging tool. Okay, don't go into your debugger or WinDBG or profiler. Just think about what you should check first. What you should check first is the fact that you are dealing with a real-world application. In a real-world application, you have logs. So you can take a look at your logs. In that case, we don't expect to see a lot of logs because this kind of contention is when your code is asking for resources, just wait a little bit that the other thread get back, so you don't log this kind of thing. And we were not able to find any log, any trace in our log system. So what should we do next?
Next, since we know that it was introduced by the release, we should check the code.
Exactly. So here we're just showing like tens of changes, but for a real release, we have hundreds of changes. And hopefully for this kind of change in the behavior, we know that it's related to a change in some specific C# patterns, like contention, like locks. And so it was quite easy to check each and every change, but unfortunately, none of them was related to a change in this C# aspect of the code. So,
okay, so at that point we are out of options. So
yes.
That's the moment to start using tools. We want more information about contention. So one good way is to use ETW because the CRR, every time there is a contention event, push a trace to ETW, and if you retrieve it, then you also have the call stack that led to that event. So there are plenty of ETW listeners available, but for this precise use case, I like to use JetBrains.trace because it has this nice representation over a timeline, which really helps you to put the event in context. So what we did is we restarted one of the servers. Then we run .trace to retrieve a trace. And there it is. Yeah. So when you activate the log contention filter, you get this view that reminds us of DNA sampling. Every one of the mark is a contention event, and every line is a thread. So you really get a grasp of what's happening. Still, it's nice, but we can't do anything from that. Simply because we don't know what is supposed to be there and what is not supposed to be there. But in this case, by chance, we've seen that it is a kind of leak. It increases over time. So what we can do is let the server run overnight, and the day after, we take another trace. So that's what we did. And that's the other trace. And just at a glance, you can see that there is a dramatic increase in the number of contention events. And just checking a few of them, and you will see that most of them are about the timer QTimer and the fire method. So that's all good. Now we know what is causing the contention, but it only raises new questions. For starters, what is timer QTimer? It sounds related to timers. And also, how could it cause contention?
Yeah, because when you end up going into your preferred debugging tools, you end up into taking a look at some method calls or some types. And here, in that case, the timer QTimer is definitely not inside the Criteo source code. So this type is related to the implementation of timers, as you said, in the base class library provided by Microsoft. So in that case, you need to take a look at the source code. So you can browse the source code from the web page, that you get the link over there, or you can go to a decompiler, which makes easier to jump from one method to another method and understand what's going on. So this is what I will do with you, changing my eyes. And yeah, and here is the timer constructor code. And here it takes a few parameters, because when you create a timer, you provide the method to call back when the timer ticks. If you need to provide additional parameters, you just give a state, and then you decide when it should tick the first time with the due time, and the last one is the period, if you want to tick on a regular period. And so after a few checks, you end up to the timer setup helper function. The timer setup helper function, what it does, it creates a timer holder, and it keeps track of the timer holder in the m_timer field. And the timer holder takes an instance of the timer QTimer, which is the one we are interested in. So let's start with the timer QTimer. The timer QTimer, it does something very simple. It keeps track of all the parameters, the 4 parameters we provided, and it stores them. After that, it inserts the new timer QTimer into a list managed by the base class library. And you see there is a lock when we need to access this list. So we know that there is a lock when we add a new timer. So let's go back to the previous code about creating a timer. And what is the role of the timer holder? So the timer holder is a tiny class that keeps track of the timer QTimer. And in addition to that, it implements a finalizer. So a finalizer, you know, it's a piece of code that the runtime ensures that after a garbage collection, after a certain amount of time, this code will be executed if there is no route pointing to these objects. So what it does, this code ensures that if you, as a developer, or someone in your team as a developer, forget to explicitly close the timer, then the timer QTimer will be removed from the big list, and no more ticks, no more callback.
So it's all nice, but you still haven't shown the fire method.
Yes, I was keeping this one for the end. So the fire method, what it does, it's quite simple. In fact, it's look into the queue. So to access the queue, it needs to get the lock. So there is a first lock, and then there is another lock just before calling the callback, just after calling the callback, because you need to resync the whole list. So we get 2 locks in this function. So we can understand that we get some contention over there.
Okay. So what we confirm is that timers can indeed cause contention. And, well, just display...
Yeah, because I like code, but sometimes it's good to have a picture to see the right relationship. So when you create a timer, you get a field that references a timer holder. The timer holder implements the finalization to ensure that even a loosey developer will be taken care of removing the timer. The timer holder references the timer QTimer. The timer QTimer is a linked list, and the linked list is managed by the timer QType of the base class library. Okay?
Okay.
So where are we?
So now the question is, since we know that timers are causing contention, where are we actually using timers? And also, there are still a few possibilities, because so we know that when the timer ticks, it causes contention. But we could either have a lot of timers in memory, or we could have just a few that are ticking very often. So to find out, it's time to use another tool, my favorite one. So it's time to start WinDBG. What we did is we took a memory dump on the server using procdump, and here it is. Well, we assume that you already have some background knowledge of those tools.
Sorry, Josh, how many of you are using WinDBG? Okay, a few of you, okay.
So what happened is that we took a memory dump, we load it in WinDBG, we load SOS, which is an extension that allows you to easily manipulate managed code, and we run depistat, which is a method a function that displays the contents of the memory in a synthetic way. So what we want specifically here is timer QTimer. So I just search it. And where is my mouse? It's there. And we can see that we have 14,000 instances of timer QTimer. So here, again, you need to know what is a normal value and an abnormal one. And thankfully, we have some experience with Criteo application. And we know that a normal value at Criteo is about 2,000 timers, which is already quite a bit. But clearly, with 14,000, we're 7 times above what we expect.
Yeah, it's something very important to keep in mind when you are doing an investigation. You need to know the context in which you are working in. Because when I joined Criteo, when I saw this kind of numbers like 2,000 timers, I was like, oh, I found a bug in the code because 2,000 timers is just crazy. And I said, no, this is what we need because we have this subsystem, this subsystem. So always keep in mind that you need to know the environment and the numbers that you are expecting to find.
Okay. So the next step is try to understand what those timers are doing. So we start by dumping all the timers. That's what this command is doing. This is a method table pointer to that type. And we have all the instances there. So if I take the first one, for instance, I click on it. It allows me to see all the fields of the timer. And here we are interested by timer callback, which is the method that is called every time the timer ticks. So if I click on it, I have the delay gate. So I personally know no easy way from WinDBG to get the method name from the method pointer. But thankfully, we have an instance method, and we can retrieve the instance from the target field. So if I click on it, we see that this timer, is used by a type that is called metametric. But if then I take another timer, so the last one, for instance, same thing. I check the callback, then the target. And this time, this is used by Kafka.batching.accumulator, which is a Kafka driver that we use at Criteo. And so we see that the timers are used for different purposes. So all we have to do now is just to go back to the list, click on each and every of the 14,000 timers, report everything on an Excel spreadsheet, and then we will have a summary of what's going on.
Sure. So we just have like 40 minutes, so maybe we can find another way.
OK, so then maybe we can script WinDBG. OK,
so we won't script debug because it will take forever. So I would instead propose to write some C# code. And I will show you that in some cases where you have huge amount of data, you can't just do it by hand because it's just useless. So you need to automate your work. And Microsoft provided a NuGet package that allows you to browse inside a memory dump or to a running processes. And this library is called CLRMD. So I've written a tiny piece of code. And in this project, I have added this NuGet to the Microsoft.diagnostics.runtime, what I'm calling CLRMD. And once you've added this to your project, you can start to write some code. And the code will simulate what Kevin has done. It's like you will be loading the dump file. Then you will get the CLR version running inside this dump. Then you will get all the heap that will contain all the instances. You will get each and every instances, checking the type name. If it's a timer callback, get access to the target field. And once you get the target field, you know the name of the type. And we'll count them. So it's exactly what I'm saying, but in C#. How many of you are doing C#? OK, it was not funny. So let's go back. You have to use the data target type, that is a static type, and the load crash dump function. You have the same to attach to a running process. Once you get the data target, you ask for the runtime. And to get the runtime, you need to give it a hint about where the MS-core DAC WKS.dll is. There is no secret here. This is the DLL that help SOS to access the information, meaning it's the data access layer required to go into the memory of a managed process. So it's exactly the same for CLRMD. It's the same DLL. Then, when you get the runtime, you ask for the heap that will contain of the instance of the type, the instance that you have allocated, and you enumerate each and every object in a for each loop. You get the type corresponding to this address. If you have done some reflection in .NET, it's exactly the same principle. You get like a type info responsible for the instance behind this address, and from this type info, you can get its name. So here we ensure that we are listing only the timer callback. And once we get the instance that are timer callback, we are looking for their underscore target field. And we are using the get field by name from this type info. And then once we get the type info, we can ask for the value behind this underscore target field. Once we get this reference, again, we ask for the object type. Once we get the object type, we ask for the name. And we add this name into a list, and the list will contain the name of the type of each instance pointing back by the timer callback. I won't send it into Excel, okay?
Really?
No, I won't.
You don't
so
know
I will
what is
just,
good for you.
Yeah, I will group by name, so I will get only the name, the list of the different names, and I will push the one with the most instances at the top of the list. Okay, I won't run it now because it's 16 gigabytes and it will take some time. So if we go to this, we will have the result of the list. And here we have the metrics.core.metermetrics with 12,708 instances. Could it be something interesting?
Yeah, so what we see here, so we have more than 12,000 instances of metermetric, and then we have the other 2,000 timers that we expected to see. So clearly now we know that it has something to do with that metermetric type, which is something that was implemented at Criteo. So it's time to dig into the code to understand what it's doing. And for simplicity's sake, we won't show the actual code, but just a summary, a big picture of what it's doing. So actually, nobody used directly the metermetric type. Instead, we have a wrapper on top of it that is called meter. It declares a property that is delegate meter that contains the metermetric instance. And then the metermetric has an underscore timer field that contains the timer. And each time the timer ticks, it calls a method that is on the metermetric. So now we get an overview of the types that are used, but we still need to understand what is keeping them alive. Why do we have 12,000 of them? And at that point, I can think of two possibilities. The first one is that we instantiate a lot of meters and we keep them alive in a list or something somewhere. The other possibility is that we don't actually keep the meters, but we forget to dispose the timers, and so they stay alive in the timer queue.
So I would say that based on what we've seen in the BCL code, the second option should not be the right one, because the timer, all the type that I show you, are just one purpose. It just have a finalizer that gets rid of the timer queue timer if a garbage collection occurred. So I would go for your first idea about the number of meter that could be a root for the metermetric. Okay.
That's something that we can check directly from WinDBG again. Where is it? Is this one? Yeah. So to find out what is using our type, there is the gc root command that is provided by SOS, but I don't really like it because it displays one single path to a root, but it doesn't give the big picture of all the types that are referencing your object. So instead, I like to use another extension that is called SOSX, and it defines a command that is named ref, and it displays all the reference to and from your type. So I just grab the nearest timer queue timer that reference metermetric.
And I would say that GC root is nice, but it's kind of slow, especially when you get a large heap, and 16 gigs is not so large. So refs is a very good option.
And so if I use ref, you can see that the only thing that is referencing it is the timer queue timer. Yeah. So it seems that your hypothesis was wrong. Still, there is another way to find out. It is to check in the memory how many meta instances we have, because if they are keeping the meta metrics, then we expect to find approximately the same number.
Like 12,000, something like this.
Yeah.
So let's go.
So I said metrics.meta.
And how many do we have?
There we go. And we have 800 of them. So clearly, it seems you may have misunderstood how the finalizer work. Okay. Still, we can make one more check.
Yes.
So if the finalizer kicks in, it will close the timer. And when the timer queue timer is closed, it sets a cancelled field to true.
Exactly.
So what we could do is enumerate the timer callback that are associated to meta metric, like you did with CLRMD. And every time check the timer to see if it has been closed.
So you want me to change the code of my sample?
No, you've done enough. I really love CLRMD, but there's something that annoys me a bit about it, is that you need to switch back and forth between Visual Studio and WinDBG, and every time you kind of lose the context, and if you don't have the project ready beforehand, you need to create it, add the NuGet package, load the crash dump, initialize everything. This is a lot of work, and this is a waste of time. So what I did instead is I wrote an extension for WinDBG that allow you to write C# code right from WinDBG with CRRMD loaded.
Okay, so all the boilerplate code that I showed you about loading the dump, it's been done by WinDBG. Getting the MS core DAC WKS, it's done by WinDBG. Then get access to the CLR, then get access to the heap. And we are just starting at that point. When you are using this extension, as you will show, you get immediately access to the heap. Yeah,
so I have that heap object that is already initialized. And also, since this is a scripting environment, we don't get the auto-completion. So to make things simpler, I also wrote a library that adds some extension method that allow you to manipulate the CRRMD object using the dynamic keyword from C#. So it's much more convenient.
Yeah, so what it means, and you will see just quite immediately, that all the stuff that I'd explained about all the type info and to get access to the field and just get the value and get the type info, it will be much, much simpler. It will be C#-like.
So what I do is first I call getProxy, which is an extension method that will return me all the timer callbacks. Then I check if they are targets. I can directly access it without doing all the get type and get value stuff. And I have another method that is that tell me what is the type of this thing. So I want it to be meta metric, sorry. So if it's a meta metric.
So it would be one of the 12,000 meta metrics that reference timer to timer.
Then we need to retrieve the timer. So in callback.target, we have the meta metric. Then remember, we have an underscore timer field that contains the timer. Then we have m_timer, which contains the timer holder. Then we have, again, m_timer, which contains the timer queue timer. And then finally, we can check the cancelled field.
So if you are a little bit confused with the timer, okay, it's normal.
So I just increase the count. And in the end, I just write the results. Hopefully. So we won't run it live because it takes more than 1 minute and we're short in time. But well, I'm just going to launch it in the background. And you can believe me on this. It will just say that all the timers, none of the timers are disposed, sorry.
OK, so none of the timers are disposed.
So it seems to confirm that the finalizers aren't working as you think they do.
OK, so what I said about finalizer, we need to verify that what I think is doing is really what it's doing. So let's see if we can double check that again. Changing my eyes. And let's try to test the timer. So here is this very simple Criteo implementation of meta metrics. Remember, we had metas that references meta metrics. But we've seen that we just have 800 instance. So let's stay at the meta metric level. So the meta metric level has the underscore field that keeps track of the timer. and I'm creating a timer that will just write tick on my console after 1 second, and then every 1 second after that. Okay? So then, in my testing application, sorry, I'm allocating an instance of the meteor matrix in these static functions, and so from that time, okay, nobody's referencing the meteor matrix. So if I'm pressing the enter button, I'm asking the garbage collector to kick in and collect all the unreferenced objects. My meteor matrix should be unreferenced at that time. So we should see tick, tick, tick. When I press enter, no tick. Do we agree on that?
Okay.
Okay? Okay, so let's run it. So we see tick,
Impressive.
tick, tick. Impressive, yeah, I know. No more tick. So maybe I was not so wrong.
Okay, so clearly we're missing something here. So let's get back to the big picture, please.
So this is the Criteo view, okay? So let's put the Criteo view with the base class library view. So we have the meter that reference the meteor matrix. We know that then the meteor matrix reference the timer reference back the meteor matrix, but in the chain of the timer, we also have the timer holder that reference the timer Q timer with all the M underscore timer, M underscore timer, N underscore timer, and forever. So this is what we have, and we know that the timer callback came from the timer Q timer back to the meteor metric. So,
okay. So what's next?
What's next? We need to add what we've checked. We've checked in the dump that the meter was not responsible of being the root of all the meter metrics. And then we checked with my tiny demo that my reading of the base class library code was not so wrong, and so the finalizer should have been kicked in and then removed the timer Q timer from the list.
Okay, so you still haven't explained why the finalizer didn't kick in.
Yeah, it's because I was very fast when I explained how the timer Q timer works with the timer holder, but some of you might have noticed that there was this timer Q that referenced the list of all the timer Q timer, and this is a static field of the type. So it's a static root that keeps reference to the timer Q timer.
Okay, so now you just have proven that there is something that is keeping the timers alive, but you still haven't explained why the finalizer isn't called. Yeah,
it's not called because here, when the timer callback references back the meteor matrix, it references then the timer holder, meaning that the timer holder for the garbage collection is referenced by something, and this something is at the very end of the refs is the queue. So, sorry, but the finalizer couldn't kick in.
Okay, it makes sense, but then why was your example in Visual Studio working?
Because I was cheating. I was cheating. So what's the difference between this very nice picture and this code? So the change is just over there. This callback is a static callback. It's not an instance callback. So what I mean is, I know.
You did that on purpose.
Yeah, I did that on purpose. So here, you just don't have this link. So if you don't have this link, it means that the meteor metric over there is no more referenced. And if it's no more referenced, when the garbage collector kicks in, you will see that no ref on the timer holder exists, and the finalizer will kick in, and will remove the timer Q timer from the list. And here we are.
Okay, so let's summarize everything that we discovered. First thing, Christophe is sneaky. Then we have a few facts. The meter type that we use at Criteo does not implement iDisposable. That's our fault. So that explains why nobody is disposing it. We also discovered that timers are immortal if they are not disposed and if they reference the class that is keeping them. And we also know that every time a timer ticks, it needs to acquire a lock. And you have this kind of double punition because you need to, the time that you need to hold the lock is longer if you have many timers. And if you have many timers, you also need to acquire it more often. So because of those two factors, it leads to a very significant increase of contention. And so if you piece everything together, then we understand why we have this increase of contention.
Good. Can we guess why we didn't find it when took a look at the source code?
Yeah. Also, Meter is a type that has been used for years at Criteo without any issue. So why suddenly? It's simply because before then we were always using Meter as singleton. So we never actually noticed that we should have disposed them. And just for that release, a developer had a use case where he needed a Meter as an instance field. And so all the code change was doing was removing the static modifier in front of the field. So without this background knowledge, it was pretty much impossible to figure out that this was the cause of the issue.
Okay.
So this is a first illustration of this process to investigate the issue, gather as much data as possible, try to understand this data, put it into context, make hypotheses, and then verify every one of your assumptions. So, and more often than not, your assumption will be wrong, and so you go back and try again until until you're finally right.
You would be very lucky if you just have one round. So
yeah, this was a very naive example. I'm sure many of you already knew how timers work and suspected that it was a dispose issue. But just to illustrate the importance of this process and especially, the last step, we prepared another case that is also a real case that happened at Criteo. It's going to be slightly more tricky, just tiny bit.
Yeah, a little bit.
So as usual, it starts from the monitoring dashboard.
So if you remember in my big dashboard, this one was tiny on the upper right, a number of exceptions. So it's the first chance exception, meaning it's a number of time in your code, you have a try catch block, and there is an exception thrown in the try, and just catch it in your catch block. So it could be a problem because it could take a lot of time to manage all these exceptions. And here you see we started from 0, which is very good, very healthy application, to like millions per minute. So it's more than 10,000 per second. So in that case, I'm expecting that the application was just not responding.
Well, incredibly enough, the application was working properly. And in fact, it took us more than 12 hours to notice that something was going wrong. So great monitoring there. So when looking at the application, it was answering requests perfectly in the allocated time. And the only thing that was different was the CPU usage, which was significantly higher. But otherwise, it was working.
OK, so again, first step of your investigation, go to the obvious. And in that case, when you get an exception and a decent developer would add a tracing line in the catch block. Okay, so I'm expecting that we would get like more than 10,000 string per second sent to our logging system. So we should have a lot of traces.
Yeah, I hope with that we have some throttling. But, well, amazingly, not a single log. So is our developer to blame? I don't know.
We need to find, yeah, we need to find. So here we are kind of stuck where with what we have at our hand, the monitoring system, the logging system, we don't have enough information. What we would need is at least the name of the exception type to figure out where we should look at in our source code. So I know a tool from sysinternal, which is called procdump. Usually we are using it to take the memory snapshot and get a dump that we've used in WinDBG. But with this very nice command line, you can ask the procdump application not to take a memory dump, but in live, list all the exceptions that are caught, try and caught in your source code. And the line is like -e for exception, 1 is for first chance exception, and then the -f is a filter about the name of the exception. And the name of the exception is a code saying, I just want a manage exception. And so with this kind of tool, first we put it on his knees. It's the first time that I've been using a sysinternal tool, and it was just becoming crazy, too many exceptions. But we were able to see that we get a lot of thread abort exception. So
yeah, that's the moment where we're starting to be a bit afraid. Were we really calling thread.abort somewhere in our code?
I hope not.
So we check all the code source and the source code, sorry. And well, I kid you not, we actually found one code that was calling thread.abort for this very application.
Cool.
But the code was removed like 1 week before the release.
Sure.
So the coincidence is so big that we actually went to a production server and decompiled the assembly to make extra sure that the call wasn't there. And yeah, it's the right version.
Yeah, that's something very important. When we tell that you gather as much information as you can, you need to trust the information. And typically in that case, when you are like, just this part of code, just at that time, you need to ensure. And the decompilation on a server is something that you shouldn't be afraid to do.
Okay, so we know that we never call thread.abort.
Yeah.
We need more information. And well, as Christophe was mentioning, program didn't really work because when we started it on a server, it was like catching the first exception, and then because of the stream of exceptions, it was kind of freezing the process, and so we wouldn't get much information from it. So as another tool, we could use ETW traces because there are some for first chance exception. But in this precise case, because we wanted more information, we actually use a remote debugger from Visual Studio that we attached to a production server.
This is good? This is good? This is bad? I don't remember. Attaching?
Well, it depends.
Okay.
If nobody noticed, then it's okay.
Okay, okay.
And from it, so of course we've seen all the thread abort exception, and from time to time we managed to see another exception, which is cannot unload abdomen exception. So that's very interesting because there are two things that we know. The first thing is whenever you unload an abdomen in .NET, it will try to abort all the threads belonging to that abdomen. So that may explain the exceptions. Another thing that we know is that our application is running on ASP.NET, and ASP.NET is known to unload the abdomen when it detects a change in the application files, so usually the configuration files. So in our case, it's probably just somebody editing the configuration file.
10,000 times per second, saving the file, saving the file.
Okay, that may be a bit far-fetched.
I'm not buying this one.
But luckily, we managed to get more information from the debugger, and namely two pieces of data, very important. The first thing is that the exception was always occurring with the same call stack.
So I'm fine with this. If we have a bug, I hope we have just one bug at the same place.
The other thing is that the exception was always occurring on the same thread.
So I'm not buying this one. On the same thread, I mean, no.
No? No. That's because you haven't seen the code. I mean, it becomes pretty obvious when you check the code. So this is the call stack where we've seen the exception. And so what it's doing is basically we have some kind of infinite loop. Inside, it's doing some processing, then it's sleeping for 15 minutes. So why the developer didn't use a timer, I'm not too sure. Maybe they were afraid of forgetting to dispose it.
Pretty sure that's the reason.
Anyway, the interesting part is a try-catch block because it was on purpose, written in a way that if the processing failed, we would retry immediately because we had good reason to think that if it failed, if it was because of an IO error, and retrying would work. But now, just imagine, we are running this code, we are either processing or sleeping, I don't know. Somebody changed the configuration file of the application, so ASP.NET unloads the domain, and so it aborts the thread. Except that, since we are in the try-catch block, we catch the thread abort exception, and then we are in an infinite loop, so we try again. But ASP.NET sees that my thread is still running, so it re-aborts it, and we recatch it, and so on, 10,000 times per second.
That's a very, very nice story, except that there is a tiny, tiny difference in the thread abort exception and how it's managed by the CLR. The thread abort exceptions is a weird beast. As you say, all your story up to the time that ASP.NET is trying to remove the abdomen and then the thread.abort is called, that's fine, okay? We get to the catch block here, and we do some tracing, whatever we want, and when the last dot is executed, the thread abort exception is rethrown by the CLR, but outside of the try. Meaning that the next time as you say, the ASP.NET will try to see that our thread is still running, do the thread abort. That time it will be good. So you should not have an infinite loop here, just one.
Okay, Christophe. You know that I value your wisdom a lot. Your diploma for university, 1989, internal artificial intelligence, buzzwords and everything. But in this precise case, you need to look at the facts. I mean, we have fact 1, 10,000 exceptions per second.
I'm fine with this one.
Fact number 2, the thread abort exceptions are always occurring in the same code stack.
Okay.
And fact number 3, the exceptions are always occurring on the same thread. And so I'm sorry, but I have to quote somebody who is more famous than me. And in short, he's saying that you are wrong.
Okay, so let's verify. Again, same step, verify. I think I know what's going on, but we'll see. Again, put your right eye, and let's try to simulate. So I have the exact same code, okay?
How convenient.
Yeah, for convenience. So I'm just working, and I will sleeping 15 minutes, but we won't have enough time. And then I will type the name of the type of the exception. And so I need to create a thread so I can abort it. Don't do it in your code, okay? Don't create thread. That's bad. So you create the thread. I'm starting the thread, so I should see the working. And then as soon as I enter on the keyboard, I should see just one exception. That's my view of the story.
And I'm saying that your console will be flooded with thread abort exceptions.
Okay, let's see. So running, working, sleeping, and
Okay, but I know that you're a tricky guy, so go back to the solution, please.
okay, it's no trick.
And I know every single of your trick. And you are running your code in debug mode. I'm sure that when running in release mode, there must be some kind of optimization kicking in, and this is causing the behavior.
Okay, let's see. Running, working, sleeping.
Okay. There must be another trick. Go back
You want to go back to Visual Studio?
No.
You don't trust me?
I know you.
Okay.
And you are running in any CPU. It turns out that per default, with any CPU, it will run in 32 bits, even if you have a 64-bit machine, except if you uncheck the prefer 32-bit option in the project.
Okay.
And I'm sure that in 64-bit, a lot of change, lot of things change. We have different pointer size, and I'm sure with a different pointer size, we have some overflow somewhere, and it's causing the issue.
Pointer size, yeah, sure.
It has
pointer size. Pretty sure everyone agree. The pointer size might be the root cause of the problem. So running, working, sleeping, and oops.
Pointer size.
It's not pointer size. No, it's not pointer size. No. So okay. So let's go back to what I think I know about the thread abort exception. And so first, you need to realize that when you call a thread abort on a particular thread, it doesn't kill the thread right now. It's kind of asynchronous. It just sets a property in the thread object, and the thread object will be checked afterward by the code in what we call a safe place. And at that time, the just-in-time compiler will generate some code that will rethrow the exception while we are sleeping or while we are working. So that's what we have.
So can you repeat that last sentence?
So I said that the just-in-time compiler is generating the... Okay.
There is another thing that changed when you are in 64-bit, is that instead of the old JIT, we are using the new ReUJIT. And when you say new, you say bugs. So maybe we have found the culprit. And there is a good way to find out.
So let's see if we can...
If you go back to Visual Studio.
Yeah, just wait, changing my eyes again.
If you open the configuration file.
Opening the configuration file, yes.
And so in the runtime node that you need to add because it's not there, you can add a configuration key, which is use legacy JIT. And you can say enabled to true. And what it does, it instructs the CLR to use the old legacy JIT, even though you are running in 64 bits. Okay, you can also force that with an environment variable.
Okay, so no change in the code, just the asking the CLR at the beginning. Okay, so running, working, sleeping, and
And that's it.
Yeah.
So we confirmed that we run into a bug from the JIT.
Okay, so we were both right. And the compiler was wrong. The just-in-time compiler was wrong. Okay. I'm okay with this.
Okay. So from there, obviously, we reported the bug to Microsoft. I don't think it has been fixed yet. I think it's still there in 4.7.1. So basically, what's happening is when the loop is written in precisely that way, the new JIT isn't inserting the safe place at the end of the catch block. And so it has time to go back at the beginning of the loop and go back in the try catch. So to fix that, then we actually added a catch thread abort exception block, and then we rethrew the exception. That's something that I never thought I would have to write someday.
No.
And yeah, and now it's working. So wrapping everything up, this was a few cases to demonstrate you well the process we go through to investigate our cases. And a few things to remember is gather as much data as possible. As long as this is not false data, then you can't have too much. The more data you have, the more time you will save. Also, don't hesitate to build your own tools whenever you need it. There are a lot of frameworks and stuff like that to help you with that. And well, the most important point is assume nothing, verify everything. I don't know about you, but we know that we are often wrong, more often than not.
Yes, especially me.
Especially you.
Yeah, sure. So it could be funny. We try to make it a little bit interactive, but often we have also seen that working in pairs, it's very, very efficient way because you have a different point of view between the two people. You don't have to know everything. The two people don't have to know everything, but it's much, much more efficient when you get stuck at one of these stages to talk to one of your colleagues and say, just explaining what you are doing, explaining what you are trying to solve, it will help you to formalize in your head having the big picture, and it's a great help. I'm also giving some resources to you. We have published a series of post blog on the Criteo's blog about CLRMD, how to use CLRMD, what you can do with them, with a lot of examples. We also have some stuff related to your extensions to WinDBG, which is very, very useful.
So I don't think you can click the link on the screen, but
no, we don't have
the
access,
slide will be published, and don't hesitate to ask us.
Yeah, you just and if you have any particular question after this session that came into your mind, you can send us email, and we'll do our best to answer. So thank you for your time.
So
I think we have plenty of time for questions. So if you have any questions, please.
We have 8 minutes.
Okay, so plenty of time. No question?
I think there's some on the left.
Yeah.
Hello, thanks. Just one question. So you said that you found out that there is some problems with memory consumption or with CPU consumption just after several days after it began. So did you consider to create some integration test or maybe unit test to measure memory consumption after each release? And if so, will it be somehow efficient? Because it looks like that we can see these problems just looking at our monitors some time ago, and for business it's not really critical. Thanks.
Well, this is a good question. Well, we have plenty of testing. We have unit testing, we have integration testing, we have sandbox testing, we have... well, on the two cases that we've shown, there was a specificity that the application was working properly in both cases. So, for instance, the leaking of the meters, that's not something that you can detect from a unit test. Likewise, that exception are thrown on your application after that ASP.NET unloads the abdomen because somebody modifies the configuration file. That requires some crazy integration testing to find out. But we do have a lot of unit testing. We don't do TDD, unfortunately, mostly because we have a custom build toolchain, and it's a bit annoying. But we try to test as much as possible before releasing.
Yeah, that's a very good point. You should try to avoid this kind of investigation because it's in production, because it's under business constraint. And as you said, I mean, unit testing, all the chain of testing is very, very important, and you need to have this in place. We've presented 2 edge cases.
Yeah.
Yeah. Any other question?
Yes, there is one.
Have you tried special memory profiler to see this graph of objects and to see static routes? Because memory profiler with UI can help to achieve this goal a little bit faster than WinDBG.
Yeah, so I can take this one just at the beginning. The way we've shown you the investigation is built for you guys to show all the different steps and all the different rules. But you are completely right. If you have some memory issue, but we were not sure we had memory issue because if you remember, the only thing that was growing was the contention rate. The memory consumption was just flat, going as usual. So we didn't start it by thinking about the memory leak because it was so tiny compared to the gigabytes that we are managing. So you're right. As soon as you guess that it might be a memory leak issue, you are completely right. Use the right tool. Use Visual Studio. You can compare dumps. You take 2 dumps, you make the diff. You take 3 dumps, you take the diff, and you see the number of instances of the time that it's just increasing. You can do it with .trace.
Memory.
.memory. So yeah, you're completely right. And that's part of the different steps. I don't know if it's the step there. When you guess that something is going wrong, and we didn't mention the fact of the memory, use the right tool. That's something very important. You're right.
That said, at Criteo, we already tried to use .memory, and we cannot use it simply because we deal with processes with more than 20 gigabytes of heap space, and dealing with more than 1,000 query per second. And .memory slows down the process so much that it just cannot do its work anymore. So that's .trace works pretty well for us, but .memory is not an option.
Yeah.
But then maybe there are other memory profilers that are much faster, I don't know.
Or you can build your own. So for example, since I graduated in 1989, I was able to build my own tool before Microsoft publishes their own tool or .trace or something like this. So I was just taking a look at the dump file, dumping everything, and just comparing the dump minus stat, and so you can achieve this. But the point is, use the right tool. Okay, don't use a profiler if it's related to something not related. Yeah. Any other question?
My question is about CLRMD. In WinDBG, we have a command analyze -v, which has a side effect. This command downloads MScore VHS of correct version of client computer. Is there any way to do it using CLRMD?
So actually there is a way to configure the symbol path from CLRMD. I don't know it by heart, so that's something you can find online. And also, I think that Dina Goldstein did a talk last year in DotNext, and she showed that. So that's something that you can check.
So at CLRMD level, you have the data target type, and you can set the options in the data target type to give an hint about where I should look for this DLL. So you have to know that this DLL comes in pair with SOS.dll, and it's present on each and every installation of .NET. So if you can't find it with the public HTTP symbols provided by Microsoft, you can go to your server machine where the dump was taken. You look at the installation of .NET, and you look for SOS, and it will be exactly in the same folder. So you can get this MS Core DAC WQS, copy it with your dump file, and ask CLRMD to look at the same folder. This is what I've done in my tiny example. If you Sorry, you need a mic. Sorry about that.
We have a problem that we don't have a server product. Our product is installed on a client, and we don't have access to client computer. We have only dumps for.
Yeah.
Okay, sorry. So I get the. So in that case, if you don't have access to the machine where the dump was taken, you should rely on the public site that is given by Microsoft, and you can set it either in the tool or in the environment variable. And you have two environment variable, one for the symbols and one for the what they call image. And the image in Windows is the TLL. So you can take a look at the Criteo blog here. Okay, look for this blog, and the first episode of the series talks about all these kind of issues and how you can get access to it. If, unfortunately, your client is using a patched version of the .NET runtime, I don't know any way to get the right version except asking them to send it to you.
So thank you very much.
You're welcome. Thank you.